So let's say if I go to slightly more complicated, no, two variable system. So there's one more nuance here in addition to whatever we just discussed. Okay. So again, I'll have similar kind of expectations that, okay. Yeah. So now instead of 2D, I have to think in terms of 3D system, no? So S, U, and V will form coordinates in the 3D, let's say, system. Okay. And now I can arbitrarily change delta U and delta V, let's say, no, given that mole number is constant, etc. Okay. And then my stability condition becomes this: U plus delta U, V plus delta V n plus S U plus delta U, V minus uh, delta Vn is less than equal to 2s uvn actually, right? And not only this, no, other combinations are also allowed. I may be increasing u, but I may be decreasing v, or I may be increasing v and decreasing u, etc. So all such combinations, eventually the entropy should be less than equal to 2s uvn, no? Okay. And just like the 1D case, of course, we can easily derive, these two conditions, local equilibrium conditions, d2s by du2 less than equal to 0, or d2s by dv2, no? So this guy, the second condition should be v2, okay? v2 is less than equal to 0. So very similar to, 2D system, I
So
think of, yeah.
d2s by du square less than 0 should be the uh, global restriction, right?
Local restriction. Global restrictions come from tangent of envelopes. Sorry, envelope of tangents. So the whole point is this delta U, no, can be large also, right?
Yes, sir.
Yeah. And only in the limit this delta U is small, I get this local condition, no?
Yes, yes.
This difference equation or the sum equation I can convert into a derivative only when delta U goes to 0, no?
Yes.
Yeah. So this guy, delta 2s by dou u2 less than equal to 0, just denote that, at that point, whichever point I will calculate it at that point, the tangent is locally above the curve. No?
Okay. Okay.
Yeah. But locally above doesn't mean that it is above the curve at all points. No, it may go a little ahead and, hit the curve and enter the curve below the curve at some other point.
Yes, yes.
Yeah. So that's why this condition is for local equilibrium, the derivative condition. Okay. And the first condition, SU plus delta U, V plus delta V, N plus SU minus delta U, V minus delta V, N less than equal to 2S. That's the global condition. Okay. So I should have written probably. Yeah. So this line which, so can you see my cursor?
Yes.
Yes, sir.
Okay. So the line where my cursor is, that's the global condition. And the other line, 1, 2, etc., that's the local condition. Okay. Okay. So these two local conditions I can also derive if I think of 2D system as effectively 1D system, no? Then also I'll get these two conditions. So the second condition is dou 2s by dou v2. Huh? So that's a typo here. Okay. Less than equal to 0. Okay. Okay. But 2D has slightly more nuances because I have a surface which is, which can, let's say have a positive slope along the x-axis and which may have a positive slope along the y-axis, but it can still have a negative slope between x and y, no, along the diagonal, let's say, as an example, right? Okay. To take care of that, there's an additional condition in 2D systems, etc., which is this basically. So dou 2s by dou u2 times dou 2s by dou v2 minus dou 2s divided by dou u dou v whole square, that has to be greater than equal to 0 basically. Okay. So this is just to ensure that, in one direction the curve is concave, the other direction the curve is concave, but in between it doesn't become convex and so. Okay. So this just ensures that. Okay. Okay. And this I give you as an exercise to show this basically. Okay. And this is essential for showing local basically this stability. So local stability or local concavity. Okay, but this still doesn't ensure the global concavity, etc., which has to be checked by doing this tangent of envelope exercise. Okay, questions till now?
Sir,
Yeah,
when we're saying that, so it has to be concave in every direction. So the local condition,
yeah,
right? So essentially, we're saying that no matter what direction you look at when you're on the point
yeah,
along the curve,
yeah, yeah,
your tangent plane must be above the
yeah. The local tangent plane must be above the curve. Yes.
right. So
Yeah,
can we model that using directional derivatives, like derivatives in different directions, and then take a double derivative along that direction, and
yeah, yeah, yeah.
then
So you do that, you will end up with this condition. Yeah,
right. So those that would be equivalent to this, right? Then
yeah, yeah. Actually, that's an exercise. Actually, you can derive this.
all right.
Okay. Yeah. See, directional derivatives involve this. So let's say my u was x, right? My v is y for a 3D coordinate
Yeah,
system,
yeah.
and
Yes, sir.
s is z basically, right? Or s is the function, let's say, right? Then the directional derivative is basically, no, you will get dou 2s by dou x, dou s by dou v, and products basically, right?
Right.
Yeah. Yeah. So that's you'll end up with the same basically thing. Okay. So you are saying they will write this in terms of curl, gradient, etc., right?
Yeah.
Yeah. So you do that and take the norm of the tangent or whatever you do to show that the tangent should be locally above this curve, etc. And you simplify that condition, you should end up here. That is my only claim.
Right. Okay.
Nothing,
Okay.
nothing more,
Okay.
nothing less. Okay. Yeah.
So,
Okay. Yeah.
so I have a doubt in energy minimization principle.
Yeah.
So if we take a two subsystems and we isolate it with the atmosphere or
Yeah.
surroundings, so doesn't the energy should be constant, right?
Yeah. Okay.
So what does it mean to have energy minimization?
Yeah. Yeah. So till now there is no energy minimization, etc. But suppose I want to remove some internal constraint of the system.
Yes, sir.
I want to change the system. No.
Yes, sir.
Right. Now, of course, I want to change the system, right? So suppose I had to, let's say, boxes of gas, no, ideal, energy E1, energy E2, etc. I connect them, rigid wall, no exchange allowed, no heat, no nothing, nothing. Environment also no exchange allowed, nothing will change, no, everything will remain constant,
Sir.
right? Right. Now suppose you allow heat change between them, right? Now suppose you allow heat exchange between them.
Yes, sir.
No, right. Okay. Now there are two conditions, right? So one you can think in terms of entropy, right? Okay.
Mhm.
And you can think in terms of entropy, easy to think. Uh, so if the total energy of the system remains constant, then the system will evolve such that, its parameters takes values such that the entropy is maximized, right? That's entropy maximization.
Yes, sir.
Now we'll come back another. Now, suppose I take this initial system, it has S1, S2, etc. and I combine them in such a way that the total entropy remains constant,
Okay.
then the thermodynamic variables will tend to take those values which minimize its internal energy.
So in this process, you are actually making the entropy of both systems constant, and you are.
Yeah.
So how it is somewhat
So physically,
unintuitive to.
physically I cannot do. I agree.
Yeah. Huh.
Physically I cannot do, right? Right. Mathematically they are equivalent.
Okay.
So doing entropy maximization, which sort of seems intuitive, because the total energy of the two system remains constant, etc.
Yes, sir.
Right? Doing that exercise is absolutely identical to doing the exercise on energy minimization. So this we can prove explicitly.
Okay, sir. Now I got it.
Okay, in Kellen it is actually proved actually. Okay,
Okay.
one of the previous chapters.
Okay, sir.
Okay, So you can prove this mathematically also, and you can prove this by argument also, etc.
Thank you.
Okay. And not only this, no, given specific kind of reservoirs, we also constructed different kind of entropies or the thermodynamic potentials,
Yes, sir.
right? The energy minimization principle almost transfers to those things also,
Okay.
right? So for a constant temperature reservoir, it's good to think in terms of enthalpy, the Helmholtz free energy, right? Minimizing Helmholtz free energy, etc. For a constant pressure reservoir, it's nice to think in terms of the enthalpy minimization. And for constant temperature, constant pressure, so almost like open air experiments, etc., it's nice to think in terms of minimizing the Gibbs free energy.
Yes.
So all of these are equivalent principles basically mathematically.
Yes.
Okay.
Thank you.
So any of these you do, you think that you are effectively doing entropy maximization. Okay.
Yes.
Okay. Okay. So these are the three local conditions for stability. And similar to the 1D case, here also you can think of tangent planes. So instead of tangent lines, you have tangent planes, etc. And the thermodynamic fundamental relation should lie on the envelope. Okay. Oh, I was already on the second page. Okay. Should lie on the uh, yeah. So the thermodynamically acceptable part of the fundamental relation should lie below the envelope of its tangent planes, just like the 1D case. Okay. Okay. So that is number one. And now just one minor trick, let's say. So we had this condition dou 2s by dou u2, right? Which should be greater than 0. No? Okay. And dou 2s by dou u2, let's say given fixed v and n, I can write as, dou by dou u, dou s by dou u, and dou s by dou u was nothing but, inverse temperature at fixed volume and fixed n basically, right? And this derivative, of course, you can write as minus 1 by t squared dou t by dou u at fixed volume and mole number, etc. And this dou u by dou t at fixed volume was nothing but Cv, no? Heat capacity per mole at constant volume. Okay, so the fact that entropy should be maximized, or dou 2s by dou v2 should be greater than 0 implies that for any thermodynamically stable system, the molar heat capacity at constant volume should be positive. Okay, and this you will see that this will also apply to other thermodynamic other similar sort of class of parameters. No, compressibility should be positive and things like that. Okay. Okay. Okay, so this all the stability criteria till now we saw in terms of the entropy, right? Okay, and then you can ask the question, can you express these stability conditions in terms of energy or in terms of other thermodynamic potentials? Okay, so of course it should be very similar. So if you think in terms of the internal energy, then entropy maximization, energy minimization, right? So there I had a concave curve, so U curve has to be convex basically, right? So here only those parts of the U curve should be allowed which will lie below the uh, envelope of the tangents, etc. Okay. Okay, and of course entropy has to, sorry, so the internal energy has to be minimized, right? So these guys, sorry, so I think the signs are wrong here. Okay, so d2u by ds2 should be less than equal to 0. Okay, where this du by ds you can write as t, so dou t by dou s should be less than equal to 0. Okay, and similarly dou 2u by dou v2. Okay, and dou u by dou v was minus p, so dou p by dou v should be less than equal to 0, I think. Okay, so the U curve has
So
to
I
be
think the signs are correct, right? Because U has to be minimized, so
yeah, sorry,
double.
so U has to be minimized. Yeah, so the signs are correct. Yeah, I agree. Thanks. Okay. Okay. Yeah, so I was mixing between the first order and the second order derivatives. Okay. Yeah, so that is in terms of, let's say, the energies basically, right? And similar to the entropy, I can write down the third condition, etc., that the in the intermediate regime, in the along the diagonal, etc., the dou u by dou 2s should not become negative, etc., and that will give you this third condition also, etc., similar to the entropy condition. Okay. Then the next question arises, what about, if you want to think of stability criteria, etc., but you are working in one of the thermodynamic potential, let's say, etc. Okay. Okay. Then that is sort of easy to see, etc., and very straightforward. But let's just recall generalized pressure. So given that capital X were extensive variables of the system, then we could generalize the generalized pressure. We could define a derivative of U with respect to the X, basically. Okay, and then when we define the corresponding potential, you remember we had a U minus Px, basically, right, for UP. Okay, and that implies that this capital X, or the extensive variable, in terms of this thermodynamic potential, you can derive as dou U with the for the thermodynamic potential divided by dou P with a minus sign, etc. Okay, and you can easily check that this holds for all the three thermodynamic potentials that we had defined, etc. Or it's just easy to see from the general principle that U of P is in most general form U, the internal energy, minus P capital X, basically. So if you start from this, then you will immediately be able to see that these two relations are sort of correct. Okay. Okay, now I take the second relation, for example, and I can do dou x by dou p. So I get a minus of dou 2u by dou p2, basically. Okay, and dou x by dou p, I can also have derived from this first relation, taken a x derivative and then inverted it, etc. That is given on the right hand side. So that is like 1 by dou 2u by dou x2. Okay, and the reason for doing all this jugglery is that the U was internal energy, remember, from this relation. Okay, so if I'm looking for dou 2u by dou x2, where x was an extensive variable, then the corresponding quantity I can write in terms of U of P, right? But it will pick up a negative sign, where this P is a intensive variable now, basically. Okay, so the sign of this quantity dou 2u, thermodynamic potential double derivative with respect to an intensive variable, is opposite to that of dou 2u by dou x2, which was the corresponding extensive variable. Okay. Okay. So I'm mixing some, yeah, okay. Yeah, okay. Or other way wise, you can think of that, if U is a convex function of X, no, so internal energy we saw was a convex function of X, then U of P, the thermodynamic potential, because it has the opposite sign in terms of the variable P, is a concave function of P. Okay, so that's the slightly mathematical algebra that we did. So, but the result now makes it very interesting. So for constant n, no, if the number of moles is constant, etc., then the thermodynamic potentials are convex functions of the extensive variables, because for extensive variables they behave almost like the energy. Okay, and concave for their intensive variables. Okay, so for example, if I think in terms of the, let's say, the enthalpy, for example, then I should get a relation which is like dou 2h by dou s2, constant pressure n, etc. This will behave very much like the energy relation, so greater than equal to 0. Okay, but if I write down this in terms of the extensive variable dou 2h by dou p2, then because this picks up a negative sign as compared to the energy, etc., this should be less than equal to 0. Similarly, for the Gibbs free, the Helmholtz free energy, so dou 2f by dou t2, which is an intensive variable, that should be negative. But dou 2f by dou v2, which is an extensive variable, that behaves like energy relation, and that is greater than equal to 0. Okay, and now for the Gibbs free energy, we have both of the variables as intensive variables, right? So dou 2g by dou t2 should be less than equal to 0, and dou 2g by dou p2 should also be less than 0, basically. Okay. So that's the stability condition in terms of all of these different these things, basically. Sorry, question? Okay. And as we already saw that, the stability condition will impose, some constraints on Cp, Cv, alpha, and kappa etc., right? So that you can show that, so Cv we already showed is greater than or equal to 0, right? And for kappa you can show by means of this relation that, dou 2f by dou v2. V is the extensive variable, so they should be greater than 0, etc. But then dou f by dou v was nothing but the pressure with a minus sign. So this just becomes dou p by dou v at a constant temperature. And this was nothing but 1 by v, the kappa T. So the compressibility of unit 1 mole of the gas basically. Okay, and that implies that the compressibility also have to be greater than 0. Right. Okay. And then, yeah, so similarly, you can use earlier whatever relations you had shown, etc. And using those, you can show that, Cp should be greater than Cv in general, and kappa T should be greater than kappa S, and both of them should be greater than 0, basically. I think, yeah. So that's it for today. I'll stop here.